Hey guys, welcome back to Introduction to Computer Networks at NTU. And you see, this Wednesday session, just like previous Wednesday sessions, we have nothing more to say. But guys, let me take you back to the announcements yesterday. So we listed many assignments yesterday. But after Polly checks the lecture progress, for this week, we will just have 3 quizzes due. But PA8 is still due, all right? Hope that you guys have already started working on PA8. Now, let's move on to the topics. Yeah, so we finished yesterday's lecture right at quiz 38. And after Polly describing the quiz, we ran out of time. So it turned out to be a take-home quiz in the end. Okay, but yeah, let's spend some more time going through it again, all right? And yeah, good morning, Felix, Yuzheng, and Jordan. Yeah, so this is quiz 38. Yeah, we have a source here, IP address being 36227.something. We somehow changed the destination of the traffic coming from this machine such that it would arrive at this machine in the middle. And this machine would change the destination address back to the original address, which is this machine. So this is the eventual destination, or the destination intended by this host from the source. Okay. And so this guy changed the destination back and changed also the source IP address. So the traffic arriving at this machine would appear that it's coming from, this machine here in the middle. And to many of you, hey, the eventual effect is that the traffic destination is changed, isn't it? Yeah, the eventual effect is that, hey, the eventual effect is the source IP address is changed. So instead of coming from 36.227 to the destination, the source is changed to this. Otherwise, everything is the same. Therefore, if we go to the discourse space, I see many of you guys says, hey, it sounds like, hey, this is working like NAT, right? The network address translation. We changed the source IP address, essentially. You know what, guys? That's indeed what NAT is doing. Let's go to the discourse space. Yeah. So the eventual effect is from 336.227. We changed the source IP address to 140.112.something, so that it would arrive at this 140.112.42.something. Okay. Yeah. So therefore, Team 16 Yuzheng said, hey, it's a NAT. You know what? The effect is indeed very much like NAT, but it's a little bit different as well, isn't it? Because if the middle box here is a NAT box, what NAT box does is just changing the source IP address. It doesn't change the destination address, isn't it? So if it's a NAT box, it's usually right at the gateway of the source. And if 36227 is indeed sending through a NAT box, the source IP address won't be much different. Won't be 140.112, isn't it? Yeah. So I enjoy very much seeing how you guys think this through, because the quiz asks, what do you think these 2 entries are for? So the first entry is with the source. The second entry is in the middle box. So Team 13 Zhengnian says, yeah, port 22 is default for SSH. And the eventual goal is to connect to the PA workstation. And you guys know that to log into PA station, you need to make sure that you're within NTU. And 140.112 is the domain. The group of IP addresses is assigned. 140.112.42 is the group of IP addresses. Oh, actually, no. 140.112 is the group of IP addresses assigned to NTU. So what that means is the PA workstation is probably restricting where the sources can be. And so if you are outside of NTU, for example, at 36.227, you'll be blocked. So the two entries redirect the external SSH connections to this middle server within 140.112, so that the source would appear to be 140.112 and therefore accepted by the PA workstation. Okay, so Team 13 actually takes in also information, clues from the quiz that, hey, that's a PA workstation. We know how to access the PA workstation. And then Team 10 follow up. Okay, redirects an SSH connection originally destined to through. So the source address is somehow translated to this one here. It's very similar to NAT, but it rewrites the IP address and the TCP port. Okay, the source IP address and the TCP ports in the end. And normal NAT map only just the port number, right? The source IP address will still appear like 36.227.something.something. Yeah, so Polly says, yeah, it's very like NAT, but it's not exactly NAT, isn't it? And Dorothy was echoing similarly. It's like NAT, but instead of only changing the IP addresses, the middle box there changes also destination address, because from the original source to this 140.112 middle box, we need to change destination. Otherwise, the traffic won't come to 140.112 in the first place. Yeah, you guys are getting closer and closer, all right? And Team 16 says, yeah, it is different, right? Because the middle box there is changing both the source and destination address. It's not just a net box. And what kind of box is that? Yeah. And Team 25, again, very observant as the previous groups. It's very much a network address translator. And Team 25, keen to avoid saying it's NAT because it's very specific, right? Pointing to the NAT protocol. But it does do network address translation, but we're translating the source IP address entirely, okay, from a global IP address somewhere else and to another global IP address. Okay, NAT is to translate from a local IP address to the global IP address. There's something different. Okay. And Felix is saying that, yeah, the middle box is like a SSH traffic proxy. And it's very much like and natting, okay, but it's different. And finally, Team 4 says it out loud. It's like a VPN server, because how you access the workstation from outside, you actually need to VPN to a machine within NTU first, and many of you use the NTU VPN service, isn't it? In fact, one can actually set up a VPN server somewhere inside, and you guys can actually connect to that VPN server. You don't need to necessarily connect to the NTU's VPN server. Okay, but anyway, as long as you have access to one of the VPN servers within 140.112, then you'll be able to access the workstation. All right? And so, yeah, Polly then reveal eventually. And now you understand a little bit more what VPN is. It's essentially NAT, but it's for hosts outside of the VPN server's local area network. Okay? So you are pretending that you are within the VPN server subnet. So people don't know exactly where you are. So if you learn that NAT provides a certain level of security because you are actually hiding behind a particular global subnet, right? VPN provides also that kind of security to you. And that's why when you travel abroad, then very often we use VPN so that it's not very clear exactly where you're from, where we're from. Okay, and it's a little bit harder for someone to find exactly who your which your IP address is, and then try to scan the ports, okay, and find backdoors into your machine. All right, good. And from I think this point on, yeah, it's easier for the rest of you to provide an answer. Yeah. So again, so this one appears that it's straightforward, but it's a little bit tricky, isn't it? It is a little bit open-ended, but eventually you find that, hey, it's a VPN. So if we go back to the Discord, if we go back to the PowerPoint slide, you will see that, hey, what the VPN client is doing is to set up an entry like this on your machine. And the VPN server here is to set up an entry like this in the VPN server. Voila. And these two entries in the routing, in the forwarding table of your machine and the VPN server is exactly to set up a tunnel, a VPN tunnel. Yeah, I see some of you guys mentioned that there's a tunnel set. Please ignore the background noise, okay? Yeah, there's probably a mailman delivering mail to me. Yeah, I mean, hey, we'll see. We'll have him or her re-delivering the mail, okay? But it's more important that we go on with the lectures, okay? So, yeah, that's essentially how the VPN servers, VPN tunnel is set up, okay? One forwarding entries at the client and one forwarding entry at the server. With that said, we can then move on to the next topic. Okay, this is the last video we want to show about generalized forwarding. Okay, and the generalized forwarding is enabled by the open flow protocol, and so that the central controller can set up these entries. So this video then is to give you an example of exactly that, from the centralized controller to set up forwarding entries across all these routers inside the network. With those examples, you see how diverse these rules can be. But you probably also see how powerful these SDN routers can be, right? It can emulate the traditional forwarding, just like the traditional routers. It can do longest prefix match. Okay, and forward it out on a particular interface. It emulates also a link layer switch, so matching on the destination MAC address and then forward the packet further. It emulates also firewalls, okay, by looking up the source IP address or destination port number and then dropping the packet or allowing packets. Yeah. One additional emulation SDN can do is this, netbox. Because what? One of the actions allowed in generalized forwarding is this, changing the content in the packet. So netbox there, okay, when there's packet coming from the local network, before you send it out, what do? We replace the source address and the source port number. So we could rewrite, okay, specific address and port number, okay, according to the need. So SDN is a very general machine that unifies a number of these different devices that we need, okay, running from the network layer and below. The last example is actually to go beyond one single SDN router to have multiple of them and forming a network like this. So you see here, this network is composed of 3 SDN routers, S1, S2, and S3. And then for each of these, talk to the controller through the open flow protocol. Right? So this controller here sometimes being also called the open flow controller. Just like the SDN routers, okay, some of them will actually call them the open flow routers. A scenario is this: let's send packets from H5 and H6 here and here, okay, from subnet 10.3 to H3 and H4. H3, H4, subnet 10.2. Okay? But through a very specific route, okay? From S3 here through S1 and then reaching S2. So we want this path. Now, the reason we want to do this in SDN is this. In traditional routing, the routing algorithm usually gives you this. Okay? If you want to send data from 10.3 subnet to 10.3 subnet, because this is only one hop. Okay? This is the shortest path. Traditional routing does not provide you the flexibility of manually configure a specific route. But hey, luckily we have the OpenFlow controller. So OpenFlow controller can actually manually configure these flow table entries to S1, S2, and S3 to allow a specific path, S3, S1, and S2. And these entries will look like this. Okay? Inside S3, the flow entry will look like this, source being from 10.3, destination being to 10.2. That's for the packet on interface 3 here. Now, the entry in S1, this router at the bottom, will look like this. If the ingress port is 1, so this is incoming port number being 1. Source 10.3, destination 10.2, that's forwarded down this interface 4. And then we manually configure S2 flow entry looking like this. Ingress port being 2. So packet is definitely coming in from here. Now, we need to separate the traffic so that it goes to H3 and H4 correspondingly. All right, so these are different IP addresses. So if we match more exact, the destination address being 10.2.0.3, then go on interface 3. So there I got this one. On the other hand, if it's 0.4, then forwarded on interface 4, therefore reaching H4. So OpenFlow, really nice and flexible. So something to add is just here. Traditional routing implements a routing algorithm. You know what? The controller can actually run a combination of manual configuration plus the routing algorithm. So it's a lot better, a lot more configurable, a lot more flexible than the traditional routing. All right, that takes us to quiz 39. You will see that we'll show how the controller can configure on top of, after the existing entries, adding some additional entries manually. All right, good. So that's, look at the example. So you see this network is very much like the example we just played in the video, isn't it? Except that we call these 3 routers now ABC. Okay. And we have 3 subnets essentially, right? So this is the first one, this is the second one, and this is the third one, right? 10.2, 10.1, and 10.3. And in each of the routers, we have already forwarding tables established. Okay, can you tell me first, okay, which way would traffic from host H6 to H4 go? So where is H6? It's here, right? Where is H4? It's here. If the traffic is coming from here and destination is here, which way would the traffic go, right? So is it this way or this way? Okay, if it's this way, hey, B will need to forward it here. So one can see that for this destination, there are definitely 2 major ways, right, going around this network. Tell me which one, okay, based on the existing forwarding tables. Q2 asks, suppose H6 needs to send traffic directly to H4 such that the delay is shorter. So that is likely asking, hey, this one up here, shorter, right, more direct, to come from H6 to H4. How can you configure, okay, add entries to any of these 3 tables such that the traffic will be enforced going this way? Okay, traffic from H6 to H4 will be enforced this way. All right, so this is quiz 39. Let's go to the to Squarespace. Guys, think about it. You guys have 3 minutes, all right? So take your time. Okay. Oh, okay. Yixin just deleted the entry. Yeah, guys, be careful. Be careful. Um, you see, on the table, we have 10.3 and 10.2. So this is one subnet within the A subnet. Okay, so this I call it a sub-subnet then. Because there's another sub-subnet, 10.3.2. So this one is 10.3.1. So we want H6 to go direct here, but we did not say that we want H5 to also go directly this way. You want to be careful, right? So if we just if we just enforce all traffic coming from A to go through interface 4, then you are also changing the routes of H5. That might not be good, right? If H5 is sending something to, for example, H2, hey, it's a little bit odd, isn't it? Would C be able to handle the traffic such that the traffic is directed back this way? So you want to be careful, isn't it? So if you have a specific purpose, you want to change the forwarding table such that only that specific purpose entry is added and all the other routes are not affected. And you can imagine a little bit that with OpenFlow, one can do a lot of manipulation and you can easily misconfigure the forwarding tables also. So it's generally harder to work with the SDN router. All right, think about it. I think you guys, yeah, there's probably a delay in the stream, right? Yeah, so in SDN, you can actually fine-tune everything because you can directly configure the forwarding table. And so one change you did might actually change entirely how the traffic flow the network. So previously, we just, ensure that the A's table, for example, let's go back here. I saw you guys saying that, hey, to make it simple, right? Minimum change, we just change this table such that it all go, yeah. So you see that you would be drawing all the traffic from here directly here. And previously was here. And it was probably this direction for a purpose, isn't it? Yeah, so if there's a specific thing that we need to tune, usually you would try to ensure that you change the table such that this is the only thing, okay, that's affected. And so how? You make it as specific as possible in the forwarding table. So let's go back to the score space. Yeah, great. So I see Yixin and many of you updated your change. You ensure that, hey, it's strictly between H6 and H4. The forwarding path goes this way, shortest path from A to C. Yeah, and therefore that traffic goes to interface 4. Otherwise, the rest keep going through forwarding interface 3, right? And B's table doesn't need to be changed. C's table doesn't need to be changed either. Okay, good. Very good. Yeah, so originally being more general like this, yeah, it will work. So this is just to make it precise. And you can see, right, setting up these SDN routers, you want to be more precise because otherwise you might be changing the policy that are previously set and you do not intend to change. Yeah, so it's actually a little bit hard to find good SDN router administrators. One needs to be careful setting up these forwarding entries so that you don't have conflicting goals as well. Okay, so one of the hot research topic is, in fact, given sort of policies that's usually written in natural languages, how to ensure that your forwarding tables don't have entries that violate any of these policies? So you will have a list of these policies written in Chinese or in English. Yeah, so we would read these policies and then configure these policies into the forwarding tables. How do you make sure that the configurations don't have a conflict between the natural language and the SDN language, the open flow language? All right, good. So you guys get the idea. Oh, I see. Hey, Yizheng here says maybe just 3.10.3.1. Yeah, okay, that would also restrict, right, between H6 given the network configuration. So this one is a little bit more relaxed, but in this particular network, it will work. Okay, and it's also precise to a degree that it's somewhat also relaxed. So guys, now you get the idea. So the goal of quiz 39 is, of course, for you to exercise how it's like to configure additional entries manually onto forwarding table using SDN router, using a central controller. But it is also to let you know that it can be tricky. It can be tricky, okay? Flexibility usually means that confusion as well. Good. Now you get the idea. But the course is not to train you guys such that you will be a very good SDN router administrator. The goal is to let you guys know that, hey, the modern routing, it's more flexible, but there comes some also complexity comes out of this flexibility. Good. I think that's good exercise, and we will move on to chapter 5. Okay, so chapter 4 is still more about forwarding part of the network layer function. Chapter 5, the routing function. So the first video is a little bit long, almost 6 minutes, but it's to give you an overview of the chapter's structure. All right. So usually these videos, they will sound trivial, very simple, but it's actually important in a way that it gives you a structural view of what's coming up. All right. So let's try to pay attention. Chapter 5, network layer, the control plane. Control plane is also what Polly likes to joke about, the better half of the data plane. Now, the reason for that is this. If you think about data plane, that forwarding function there, what it does is simply, right, for each incoming packet, do a table lookup, and you know what to do with the packet. Okay, so for each incoming packet, one table lookup, and that's it. There's nothing really intelligent about it, right? The only thing the forwarding is doing just table lookup, and it's just pattern matching, right? But hey, we are sending all sorts of packets coming from different sources, and they're going to different destinations, right? You cannot be sending these packets to arbitrary directions and hope that they will reach the destination. No. So that table there is really where the intelligence is. That is really, okay, guiding the packets to go to the right direction, eventually reaching the destination. So the data plane, the forwarding function, although very busy, working tirelessly, trying to forward packets, okay, but it's actually simple. Stupid. Intelligence is right here in the control plane, and the intelligence is implemented using these, the routing algorithms. Okay, so routing here, what I meant as a function is to find a path, okay, for a particular source to be able to send packets to a particular destination, or to find a path so that packets belonging to a flow can flow through the network, okay, with the right amount of resources reserved. Okay, so routing algorithm there. Very intelligent. Okay. So in fact, the first part of chapter 5 is going to sound a little bit like you're attending an algorithm course. So Polly will be speaking about 2 general routing algorithms. Okay, so they are graph algorithms. So provided a graph, okay, if you think about it, a network having machines connected by cables is a graph, right? Points connected by lines. So provided a graph, we could calculate, we could compute the shortest path from one arbitrary point to another point. That is what the magic of the routing algorithms are. So these 2 general routing algorithms will be implemented on the internet as 2 routing protocols, OSPF and BGP. We'll talk about these routing protocols later after we finish describing the general algorithm. Now, these routing protocols are running on the traditional routers, where you have the data plane and the control plane. So the routing algorithm is running in the control plane. Okay? The control plane of each router might be communicating with the control plane of other routers. And together, they complete the task of calculating routes, and in turn, generating the forwarding table, and in turn, install the forwarding table to the data plane, and in turn, the forwarding function, okay, can be working really fast. Now, the new model of doing routing is called SDN, software-defined networking. So the one that's doing the route computation is the controller. Okay, this is also known as the remote controller, because in SDN, okay, the model is slightly different. You still have the data plane doing the forwarding, but the control plane is implemented outside of the routers. Okay? In fact, powerful machines, somewhere remote. That's why these controllers are also called the remote controllers. Okay? And between the remote controllers, routing, okay, is being done where we generate the flow tables. And the CA, the control agent, now in the data plane, okay, that's taking in all these tables being transferred from the remote controller. Okay? In between, there's this open flow protocol. Now you should know after chapter 4. So after the control agent receiving the flow table, the flow table gets installed, and therefore the SDN routers can do flow table lookup, okay, do generalized forwarding. Now, the remote controller here, okay, it's actually quite general. Inside the remote controller, you could implement multiple routing algorithms, such as the one used by the traditional routing. You can also implement other routing algorithms, and in addition to all these routing algorithms that could be running simultaneously, and you pick and choose a particular route for a particular pair of source and destination. You could also actually specify preferences, or specify costs, okay, or specify other functions. Okay, so SDN's remote controller, being very general, okay, is actually working like pretty much a regular computer, okay, or expensive servers.
So on these SDN remote controller, okay, we run operating systems, elaborated operating systems, such as ODL or ONOS. Okay, so these are two different operating system architectures, and both have big camps of supporters. So yeah, SDN routers are made available today that both operating systems can be installed, okay, to support route computation, flexible route generation, flexible flow table generation. Okay. So these protocols, as well as these two, okay, of the technical components in chapter 5 concern the routing function, the second important function in the network layer. In the control plane, okay, we also implement some protocols that is to do this, the management, okay. So management of the routers or the routes or the packets traveling certain routes. Okay, so those are called the ICMP. So ICMP there is to allow generation of special messages from the routers or from the host to the routers, and routers generating something back. So these are there for the network admin to sort of probe the network to find out, okay, where and what might be going wrong inside the network. SNMP. Okay, so SNMP there, the management protocol is more there continuously tracking, okay, the statistics of the network. For example, number of packets traversing a router, number of packets traversing a route, okay, number of routes on a router, and things like that. So that the network admin can know better the status of the routers, status of the routes. Okay, so again, for management purpose.
All right, so for the rest of chapter 5, you see that in solid black, we'll be spending a lot of time going through these traditional routing algorithms. And then the SDN control plane, we'll talk about it, but there's not much more to talk about except that it can run the traditional routing algorithm. It can also do manual configuration, right? It's just that how you translate from the natural language to open flow instructions. So that's chapter 5. And let's start from going over, okay, let's start by, hey, next topic, routing algorithm overview, all right? So we'll first by abstracting the routing problem as a graph problem. You see, we have a network. Inside the network, we have routers. Okay, so consider these routers as vertices, and then the link connecting the routers as edges. So you have vertices and edges, and the vertices are connected through these edges. You have a graph. Okay. I don't know how many of you have already taken courses such as algorithm or maybe more advanced data structure. You might have learned some graph algorithms. And some of the graph algorithms will allow us to discover the shortest path from one vertex to another vertices on a graph. So finding a route, okay, in a network is essentially running one of these shortest path algorithms, meaning finding a path and hopefully finding the best path or least cost path possible. Now, as to what causes, okay, in a network, that can actually be defined, okay, flexibly. All right, so the first video is to do this translation from a network to a graph first, and the objective, and define the objective of the routing algorithms.
Now the core of chapter 5, the routing algorithms, or the routing protocols. So a good routing protocol there should be able to identify good paths or good routes from the sending host to the receiving host through this network of interconnected routers in the middle. So that is essentially trying to come up with a path. Okay? A path is a sequence of routers, one connected to another, and connecting the initial source to the final destination, okay, such that this path here is the least in cost, so we pay the least, or the delay is the shortest, or the promised bandwidth there is the highest, therefore the congestion level will be the lowest. Okay, so finding a good path, that is the goal of a good routing protocol or routing algorithm. It's also one of the top 10 problems in computer network, just like reliable data transfer, just like congestion control. In the next couple slides, Polly is going to introduce this new term called graph. A network okay, of routers interconnected by links is a graph. So let's focus on the network in the middle here. What you see is that we have router U, router V, W, X, Y, Z. So we have a set of routers, okay, and there are 6 of them. Now between the routers, we have also links. So link UV here connects router U and router V. Similarly, UX here connects router U and router X. VX, V here, X here. Yeah, VX is the link connecting router V and router X. Link VW, connecting router V and router W. So you see we can go over all the links defined here, and this forms the set of links interconnecting the routers. And coincidentally, a graph is also defined in a very, very similar way. A graph consists of the set of nodes and the set of edges interconnecting the nodes. So N here stands for nodes, and here E here stands for edge. So if you consider the routers being nodes, yeah, so the set of router here is the N here. If you consider links being the edges, then E here, okay, is the set of the edges. With the set of nodes, set of edges interconnecting the nodes, we do have a graph. So a network here is also a graph. And such an abstraction is really, really convenient later on when we're introducing the algorithm. It could also be useful when we're talking about other kinds of networks. Okay. So for example, in the application layer, chapter 2, for P2P, okay, you see there, okay, there are peers here, there, all around the internet. And we establish connections between the peers, right? So we could do what? P2P communication. So if you consider each of these peers as a node, and these TCP connections or UDP connections connecting the peers as an edge, there, you also have a graph. You also have a P2P network. And you can also run a routing algorithm, okay, on a P2P network, if you think about it. And now we can talk about this other thing, okay, it's called the link cost. So associated with each link, okay, on a graph like this, you see a number nearby, that is the link cost. To denote the cost of a link connecting router X to X prime, we use this notation, CXX prime. So CWZ, connecting router W to router Z, the link here, yeah, the cost of that link is 5. Right? That cost, okay, can be set in a variety of ways. For example, set it as the inverse of the bandwidth available. You can also set it to the inverse of the traffic level. You could also set it simply to a constant, such as 1. Every link costs the same, 1. Okay. So that is link cost. Now the cost of a pass, okay, is essentially also very simple. From the source x1 to the destination xp, it's the sum, okay, of all the link costs connecting from the source to each of the routers along the path, all the way till the destination. So it's the sum of the costs from the source to the first hub router, x2, c, x1, x2, plus c, the first router to the second router, x2, x3, and so on and so forth until the last router, xp minus 1, to the final destination. Okay. So let me use an example. Let's say traversing from U to Z, and we take this path. Yeah. The cost of the path will then be adding 2 to 3 to 5, and that will be 10 here. All right. So the goal of routing algorithm is essentially to find the least cost path, okay, between a pair of nodes, okay, from source to destination.
Right, and next is let's overview the two routing algorithms or graph algorithms that has been used on the internet. So one is called link state, the other is called distance vector. Link state requires global information, the entire network, okay, information to do computation. But the distance vector, okay, the second kind, requires only local information. It does not require information of the whole network. Okay, so here's the overview video of these two routing algorithms.
And Polly will be introducing two routing algorithms next. First is called the link state algorithm, second, distance vector. The link state routing works this way. Inside the network, each router, okay, in the router, it implements an algorithm before this algorithm can be triggered. router needs to wait to have the complete topology and link cost information. What I meant by complete topology is this. Each router will need to know N, the set of routers composing the network, E, the set of links interconnecting all these routers in the network, and link costs of all the links connecting the routers in the network. So each router needs to know how the network looks like globally before the routing algorithm can be triggered. Another characteristic is this. The link state routing algorithm will run in just one pass. So provided global information of the network, trigger routing, route computes, and completes. As a result, each router not only knows the best route to all possible destinations, it actually knows all the best routes from arbitrary source in the network to arbitrary destination in the network. So the router there, very informative, knows how the network is like entirely and knows all the paths for all the possible destinations and source pairs. On the contrary, in distance vector, routers no longer require global information. The routers also do not do one-pass route computation. Rather, the router only needs local information, namely, a router only needs to know how it's physically connected to the immediate neighboring routers and the link cost to the neighboring routers. And that's all. The route computation begins. With very minimum information, the computation gives you suboptimal results. So each router there, after running the distance vector algorithm, will know just slightly better than nothing. And that information is definitely not quite good enough to give us the least cost paths. So what distance vector routing does is each router will then, after some initial computation, exchange the result of the computation to the neighboring routers. Neighboring routers would also exchange what they know slightly better to the router here. Now, this router in the middle, after receiving slightly better information from the neighboring routers, can recompute and see if even better paths have been discovered. So if the router again discover better paths, then tell the good news to the neighbors. Similarly, neighbors would also tell slightly more information to the router. As such exchange expand, gradually traveling through the network. All the routers in the end learn about converge to the least cost path. So the process you see, computation, exchange, computation again, exchange again, computation yet again, exchange yet again. So the process is very iterative. It's going to take some time, but eventually, as the information propagates through the network, everyone converges to the least cost path. So a very different model of doing route computation. Link state routing being global, distance vector routing being local. Now, another way of classifying the routing algorithms is this, by judging at how the routes are being updated. Static routing is not updating the routes. So this is only for the network that is not changing frequently. And we know that this kind of network doesn't really exist these days. So all the routing algorithms that we're introducing are working this way, dynamic. That is also saying that routes can change, link costs can change. Routers could suddenly be dead and then or suddenly being booted up. So we'll try to update these routes, repeat the computation periodically, or in case we detect there's a link cost change or no change, or some other changes.
All right, so link state and distance vector. One requires global information, but you can do the computation quickly given that all the information is there. Distance vector requires only local information. It seems that you get to save a lot of memory without maintaining information of the entire network. But it's done in an iterative way. It would take some time for one really discovering the best routes. So you see a little bit of the trade-off between the two algorithms. All right. And guys, it's time to take a break. After the break, we'll come back to learn more about the first algorithm, link state routing. All right. So break starts. It's now 11:12. We'll resume 11:22. it's time. Let's resume the lecture. And by the way, guys, look at the chat box. Polly has finally assigned a pop-up queue. It's asking, after the overview of these two algorithms, link state versus distance vector, which one do you like better? Oh, okay, I see Bo Yuan here. Oh, link state, because I think having global information can make the cost reach optimum minimum faster. Oh yeah, right? Because you heard from the overview of two algorithm video that for the second kind, distance vector, it's iterative. So it will take some time until finally a router learns about the best information of the part of the network that's farther away. Okay, good. Bo Yuan, very good. And now, let's begin introducing link state routing. And the first video is exactly to give you an overview.
Now, finally, the link state routing algorithm. So what's implemented there essentially is the Dijkstra's shortest path algorithm. This is very well known in graph theory. Okay? Again, as mentioned, in order for this algorithm to work, we need the global information, network topology, link cost. And this information is acquired by sending these link state broadcast messages. So each router will be sending information about itself and how it connects to other neighboring routers and what is the link cost to the neighboring routers. And that information from each router needs to be broadcast around the entire network until every router on the network receives link state broadcast report from every other router. Okay, then all nodes will converge to the same information, same network topology link cost, and therefore beginning to compute the least cost path. So once the computation is done, we get the forwarding table to install to the data plane. Okay. Now, something extra is this. The computation itself is iterative, okay? But it's not working iterative like the distance vector. The distance vector's iteration is computation, exchange, and computation, exchange. The computation part and the exchange part is being iterative to each other. The iterative here meant, okay, there's a loop. Okay? The computation is actually working a loop, iterating through multiple loops. Therefore, okay, if we have k destinations, it takes 8 loops or 8 iterations to complete the route. Okay, so, yeah, the algorithm itself is looping within itself, but the computation will be done, okay, all at once without exchanging further information with the neighboring routers. Let me introduce these notations before I bring up the pseudocode for the Dijkstra algorithm. First is CAB. This is the cost of the link connecting router A and B. You should know already. Yeah. What's a little bit surprising to you is this. The cost, CAB, could be infinite, okay, because there's no direct link connecting the two routers, and therefore the cost is infinite. Second notation is this, DD. Okay, small d here is indicating that for a particular destination, the path from this router doing the computation to this destination, what is the cost of the path currently? Okay. So capital D here actually stands for distance. This is also saying what is the current distance to a particular destination D for this router doing the computation. Now, PD here, D again is the destination, okay, and PD is to indicate for this router to reach the destination D, okay, along all the routers on the path. What is the previous router before reaching D? Okay, so predecessor node along the path until reaching D. And prime is the set of nodes whose least cost is already known.
All right, so that was the intro. What's more important are the 4 special notations. C, A, B, that's the link cost between node and B, all right? And there's big D, that is the distance to a particular destination from this router doing the calculation. And then there's a predecessor node, right? So that meant to say that, hey, which is the previous router in order to reach the destination? No, this one is a little bit harder to understand, but this one is actually important and used, okay, in the routing algorithm. Later on, you will see a little bit better what P is used and how to better interpret what P is. And last is just this N prime, okay. In this algorithm we use, which is Dijkstra algorithm, in case you've learned about it, so this n prime is the set of routers that we have already traversed, we have explored, try to find the best route to it. Okay, so these four notations important because coming up next is the algorithm, and you will see these four notations again and again. All right, and this video is a little bit long, almost 6 minutes, but the first part is to talk about the initialization process. And then the second part, there's an iterative process. Okay, so there's a for loop essentially. And inside the for loop, we'll gradually add nodes into the n prime set. Okay, so we will traverse eventually all the vertices on the graph. Okay, so that n prime will gradually extend and extend to cover the entire vertex set. All right, two parts, initialization and iterative. All right, guys, you might want to pay attention to this video so that you just need to listen to it once. Okay. 6 minutes. Okay, let's see.
So here's the pseudocode of the Dijkstra algorithm. There are two phases, the initialization phase and the looping phase. The looping phase looks really complicated, so let's not worry about that part yet and focus on the easier part, the initialization phase. So what we're doing first is to initialize the n prime, the set of nodes we know already the best route to. And we are quickly including A. The reason is this. Whenever we execute once the Dijkstra algorithm, we give also the source of the path. So A here is the source of the path we're trying to discover. In fact, after running through a Dijkstra algorithm, we will discover, okay, the shortest path to every other node in the network. Now the source, in case A is also its destination, hey, it's trivial, isn't it? We just don't send it down. Send it to 127.0.0.1, the IP address for the local host. So we can initialize n prime to just the source node safely. Second thing we do is actually a for loop here. Okay, inside the for loop, we'll go through all the nodes, okay, in the network other than the source. So all other nodes, okay, and for each node, okay, B, we check whether it's directly connected to the source. If it does, we've discovered a way to go to this particular destination, isn't it? And the distance to it is the link cost between node A and node B. Now, if the node is not adjacent to A, then it's going to trigger this line here. No route has been discovered yet to this destination B. Therefore, distance to the destination, infinite. Okay. Now, from the description, you probably also see, in order to find all pair shortest path, you need to repeat the Dijkstra algorithm, providing a different source address. Okay. Now the exciting part, the looping phase. It looks a bit complicated, but if you focus first here, okay, the loop is going to go until all the nodes are in the n prime set. That is also saying that the loop is going to go until all the shortest paths have been discovered. Okay, the shortest paths to all the nodes have been discovered. And you probably guess that, hey, one of the things that will be changing in the loop is the n prime set. Okay. Yeah, indeed. Okay, the first part in the loop is exactly to do that. We are gradually adding nodes into the n prime set. Okay, and the node we pick to add is this. Okay, the node such that the distance to it is currently the minimum. Because adding this I to n prime set is also saying that the best route to I is already discovered. Okay, so why is the minimum di here is suggesting that the best route, this is also the shortest distance to I. Now, think. Originally, okay, we have A in the n prime set. Okay, the D, B there existing with, significant values are these. The nodes directly connected to the source. And therefore, the distance to each of these nodes, okay, is the link cost. Now, in the loop, okay, the first two lines here is going to include what? The node with the smallest link cost to the source into the n prime set. Is that making sense? Is the shortest distance, okay, to that particular node exactly that? Is there a way to discover another path to that node that is going to be lower than the link cost between A and I? Not possible, right? Because all the other links cost is higher. If there exists another path to I, the cost is definitely going to be longer than this because all the other link costs are higher already. Okay? So di here is indeed the minimum, and I here we've already discovered the shortest path. So it's safe to include it into n prime, in fact. Now, having added I to the n prime set, this is also saying that we already discovered the shortest path to I, and the shortest distance is di. So I know there is something really nice to exploit. Okay? Through I, we can potentially discover shorter paths to other nodes. Okay? We have not yet discovered the shortest path. Okay? So what we're doing here next is to go over for all j nodes that are directly connected to I. So for all the neighbors of I, and not yet in n prime. So all the neighbors of I that we have not yet discovered the shortest path, then we update dj. Okay, and that is what this formula is saying. Okay. So the new dj is the minimum of the two, the existing dj and okay, the distance to go okay, from j directly to I and di. So the shortest distance from I to the source. So di plus Cij. So this is what the comment is saying. The new cost to j is either the all cost to j or the shortest path to I plus the link cost from I to j. So what we're doing there is to update dj. Okay, if there is a shorter path, that's just editing. If there's a shorter path, that's override the bad path. Okay, things like that. So you see, what we're doing in the looping phase is actually not much different from what we're doing in the initialization phase. So this part of the looping actually corresponds to this part of the initialization, isn't it? Okay, including nodes that we know for sure. Okay, what is the shortest path? And then here actually corresponds to this. Okay, try to discover the shortest path possible. Okay, by updating based on the information that is known.
All right, so that was the algorithm. Nori, that's exercise the algorithm through an example. So here's the first part. So imagine, right? So we will be doing first the initialization phase, okay? And in this example, we'll also try to do the first iteration.
So that was the walkthrough of the pseudocode. I know it might appear a bit fuzzy to you. Let's go over a concrete example. So in the example, again, we have 6 routers and their links. Each link comes with a cost. And let's assume U is the source, and Dijkstra is going to do the computation starting from U. Now, the initialization phase says let's include the source into the n prime. Therefore, we see U here appearing in n prime. Next thing is to go over all other nodes. Okay. So X, W, V, Y, Z. Those who are adjacent to U, then we set the minimum distance to it, set the predecessor to reach it. Otherwise, if they are not directly adjacent to U, set the distance to infinite. So for Y and Z, we'll see, this should be infinite. And for VWX, V, the distance to V should be what? The link cost between the source and V. So between U, V, link cost 7. So 7 should appear here. The predecessor for such a path definitely going to be A, because we just added A to the n prime set, right? And we're reaching V through a direct link. Therefore, the previous node must be the source, U. For W, link cost being 3, so 3 here, predecessor, again, U. For X, link cost being 5, and predecessor, U. And 7U, 3U, 5U, infinite, infinite. Okay, so we just finished initialization phase of the Dijkstra algorithm on the example. Now, entering the looping phase. First thing we do in the looping phase is what? To find the I that is not yet in n prime, such that the shortest distance to I is the minimum, and we add that I to n prime. Alright, so let's go over the di. Okay. 7, 3, 5, infinite, infinite. Which one is the minimum? 3 here is the minimum. Therefore, I is W this time, and we'll include I into the n prime set. That is why Next, we see u and w both in the n prime set. And then we can now do the second thing we do in the loop. We'll update the minimum cost. And we're going to do this for all the nodes adjacent to, what is the I being added there? W, right? So we'll go over all the nodes adjacent to W. Okay, and that is now already in n prime. So who are the nodes adjacent to W? X, Y, V, oh wait, oh yeah, Y disconnected, okay, because there's one link here, and U, all right. But you know what? U is already in the n prime set, so let's remove this. So there's just 3 nodes, okay, can potentially be J, and we need to update the minimum distance and the predecessor node. So what we'll be doing here is to exploit W here, okay, as a hopping node. So V here, okay, there's another path, right? Originally we had this direct link, but now there's an alternative path through W, which is what? 3 plus 3, okay, the minimum distance to W plus the link cost between V and W. And that is how much? 6. Is 6 better than the existing minimum distance to W? Existing minimum distance to W, existing minimum distance to V is 7, and that is indeed better. Okay, so 6. And in case it's better, the new path is better, we'll set the predecessor to the new node we're hopping through. So V is now taking W as the predecessor, and the cost, minimum cost from the source, is only 6. Second neighbor, Y. Previously, dy infinite. Currently, if we use W as a hopping node, 3 plus the link cost between W, Y, 8, together 11. Obviously better than infinite, and the predecessor is what? W. Third neighbor of W, X. Exploiting W as the platform, hopping, and then adding the link cost between X and W, that is 7. Is 7 better than dx? Dx was 5, 7. Oh, yeah, in X's case, not better, so we'll keep 5 here. Z not being connected, it will remain the same, so remaining infinite. And therefore, we should see 6W here, 5U here, 11W here, and infinite here.
All right, so initialization phase and first of the iterations. Okay, and Nori in the second video will continue to develop all the iterations.
So what do we do next? Well, we're in the loop, and we are not in the condition to end the loop yet, so we're not yet done. We have only U and W in n prime. Okay, there are more nodes, okay, we could consider adding to the n prime set. And the way we add to the n prime set is to pick I such that the I is the minimum. So dv6, dx5, dy11, dz infinity, which one is the minimum? Yeah, x is the one we're picking this time. So we'll include x into the n prime set. And we see there, x here is the I. So we'll be examining all the nodes adjacent to x next. So x is here. The adjacent nodes include u, w, y, and z. But you see, yeah, we'll be going over all the nodes adjacent to y, but not yet in n prime. U and w are already in n prime, so we will not be updating du, not updating dw. So let's update dy. The way to do it is to follow the formula. What is dy now? The current cost, 11. What is the new rediscovered path cost? What is the new path? Well, one can actually go to x and then using x as a hopping platform to reach y. And the total cost is 5 plus 7. That is 12. This time, the new path is actually not better than the existing path. So we keep 11w here. The other neighbor, z. Okay, what is the current cost? Infinite. So infinite here. Cost to x is 5. And the link cost from x to z, 9. So the new path discovered is 14. And the predecessor is x, which is better than infinite. So 40, x here. Now, v is not even a neighbor of x, so we'll just not update dv and pv at all. So, and that's why we see 6w here, 11w here, and 14x here. So this is the second iteration in the loop. And next, pick I again with the minimum di. 6, 11, 14. Therefore, we include this time v into the n prime set. So 6 here included, v included to the n prime set. And therefore, the I is v. So I here. We'll go over all the adjacent nodes of v, which includes u, w, and y. And that's now already in n prime, so that excludes u and w. The only node that we need to actually update the d for is y. So we'll be updating dy. Existing dy, 11, right here. So if v here is the hopping platform, the cost to go to v, the cost to go to v is actually what? 6, okay, through w. The link cost from v to y is what? 4. So 6 plus 4, 10. Is 10 better than 11? Yes, it is. So let's update it. And this time the predecessor is what? V. Okay, so that is also saying this path here was no longer good, and this is actually a shorter path. Now z is not directly adjacent to v, so we just leave this entry down. That is why we see 10v and 11x. Good, so yet another loop. We pick another I with the minimum di. 10, 14, therefore we pick y next, and y is included into the n prime set. So y is our I this time, so y here. Go through all the adjacent nodes that are not already in n prime, so x already in n prime, w already in n prime, v already in n prime. The only one that is not in n prime is z. So let's try to update the distance to z. And again, follow the formula. Existing distance to z is 14, so 14 here. Using y as a hopping platform, which says, the minimum distance is 10, and the predecessor is v, so it's this path here. And we are adding the link cost from y to z, which is 2. 10 plus 2, 12. Oh wow, so this new path here is better than the existing path, so let's update this to 12, and the predecessor is what? Y this time. And so we should see 12 and y here, and the last loop is to include the only remaining node, that is y, actually that is z here, okay, into the n prime set. And there are no neighbors adjacent to z that's not yet in n prime. So this part we don't have to execute for the last iteration. Okay. And by now we've completed the Dijkstra's shortest path algorithm, okay, for an example of 6 nodes.
All right, so you see, trying to run all the iterations out, it's very routine, gets a little bit boring, all right? So that is what computer does better. They can repeat the same thing again and again and again, and much faster than the human brains do. So, power of computers. There's one more video. Because after Dijkstra algorithm, of course, we seem to get what is the shortest path to all the destinations out there from the source. But hey, the goal here, we're handling a routing table establishment problem. So what is the forwarding table after Dijkstra calculation? So the last video is to show that eventually, after the Dijkstra algorithm, we build the shortest path tree from the source, from the router doing the computation. And from this shortest path tree, with the predecessor information, how one established the forwarding table for the source node to all the destination possibles on the network. So this video, let me see. A bit short, 1.5 minutes. And right after this, we'll do quiz 40. And there'll be another network that it will be exercising the Dijkstra algorithm or the link state routing protocol through.
Just a couple more notes to construct the shortest path to a particular destination from the source. Say from U to Z. Okay, what one needs to do is just to track the predecessor node, okay, and that's trace it all the way back to the source. So Z is the destination. That's traced back from the predecessor of Z. which is indicated here being y. And who's the predecessor of y? Yeah, it's stated here, which is v. Who's the predecessor of v? Stated here, w. Who's the predecessor of w? U. That is the source. Yeah, therefore you see, this is the shortest path from u to z. The shortest path to x, yeah, indicated by the predecessor, which is u itself. And so we could actually reconstruct the shortest path by just tracing back the predecessors. And you see also here, if we trace back, okay, for all possible destinations to the source, you see also a tree rooted from the source u, okay, to all the destinations. And this is indicating also the shortest path to all the destinations. And such a tree is also called the shortest path tree. And Dijkstra algorithm there is also used to calculate, okay, to generate such a shortest path tree. Second note, the d values, okay, when we're picking the I, can have a tie. So in that case, we just have to break the tie and picking one of those.
All right, and that takes us to quiz 40. So in quiz 40, you're seeing a different network. All right. So there will be two steps. Step 0 is to do the initialization, okay, of this derivation table. Step 0. And of course, we start by including the source node, which is u here. All right. So can you follow the initialization part of the algorithm and fill this row up? Second step, okay, or step 1. Okay, so that is here. So this is the first iteration of the looping phase. All right, so then you try to find I that's not yet in n prime, such that the distance is the minimum. Okay, and so you will need to check among all the entries you have developed in step 0, which one is the minimum, which d is the minimum, right? And you include that node into the n prime and continue and do this looping thing and update the DJ for all the rest of the nodes adjacent to I. All right, that's exercise. So this one might take some time. How about 6 minutes? Okay, guys, use the time to exercise. So let's go to the discourse space. There, so you see quiz 40, the two steps are already on the quiz 40 channel. So let's start counting time, 6 minutes. Okay, Polly has not yet developed the tables herself, so I'll be doing it with you guys. All right, so let's start counting time. Adjacent to A, B adjacent to U. So let's see, 1 link, 2 link, 3 link. So these 3 nodes are adjacent to U. Okay, and we make DW, link cost 5. And this is here. By the way, guys, if it will be easier, you can also actually write it in your notes and take a photo of that and upload. Okay. So we have already 1u infinite, 2u, 5u, 1u infinite, and infinite. So which one is the minimum? This one. So we include x here. Okay, I is x, where di1 is the minimum. Update dj for all j adjacent to I. So x is here, and u we have already traversed. So we want to update for all dj. So 1 link, 2, 3, 4. So this we ignore, it's already done. So we just need to update dj, dw, and dy. dv, sorry, dv here. dv. Okay, so this is 2. And from v to u, it was 2. And together 4. Okay, so 4 versus 2. Not better, so we keep 2u here. Now w. 3 plus 5. Okay. Versus 5. And so we keep 5u here, right? And y? This is oh, sorry, I was wrong. So no. It's 1 plus 3, so this should be 4. And going through x. Ooh. And this is 1 plus 2. So it was 2 to 3. And then 5 to 4. Okay, so we update. So this one is okay. So we update this to 4x. And y is now connected to x. So 1 plus 1, 2. 2 versus infinity. Yeah, 2 better. And then we go through x. These are not connected. So this should be ux, 2u, 4x, 2x, and infinity. Okay, let's see. ux, 2u, 4x, 2x, infinity. Okay, so 正年 just continue to write the same thing, that's okay. 2u, 4x, 1u, 2x, very good. Very good. All right, guys. So this one is indeed straightforward, right? So it can take some time, but the rules are clear. So having a pseudocode is like telling you pretty much what the solutions are, all right? So you just need to exercise so that the next time when you're developing, it will go faster, particularly, for example, in the exams, isn't it? And yeah, I'm sure that given more time, you guys will be able to finish quiz 45. So we move on to talk about the issues. And I think there was some discussion on the chat box saying that, hey, after going through the algorithm, the pseudocode, it sounds familiar. Sounds like what you guys are doing in the algorithm class. And so the next step is to analyze the algorithm. You know what? Yes, let's analyze the performance of the algorithm next. You will see that, hey, the computation cost is big O n square. Okay, so this video, 3.5 minutes.
Now with the two examples walked through, you see the Dijkstra's algorithm, although look a bit cryptic at the beginning, it's in fact quite straightforward. Initialization phase, 2 steps. Looping phase, 2 steps. Looping phase is the one that we take multiple iterations, we spend more time with. So that is going to bound the complexity of the Dijkstra algorithm. And within the looping phase in each iteration, which of the steps is taking the most time? Yeah, the second step. Inside the second step, we're actually checking all nodes j. Okay, that is adjacent to the node we just added into n prime. Okay. And inside each iteration in the inner for loop, what we do is this, the min operation. And this is in fact to compare the value of the current shortest path to the newly discovered path, right? So d to I plus the link cost between ij. So it's a comparison between this value and this value. So you have the looping phase, and inside there's an inner loop that is doing a lot of these value comparisons. Now, if we consider a fully connected network, that is the worst case for Dijkstra algorithm. Inside the network, there are n nodes. Okay. In the first iteration, so only the source is in the n prime. How many j's is connected to the source? Yeah, it's fully connected. Therefore, n minus 1 nodes, they will all be j, and we'll need to do min for each of these j. First iteration, we'll need to do n minus 1 comparison. Second iteration, how many? Because there's one more node being included into n prime, so number of j in the second iteration, only n minus 2. Third iteration, and we can go on until the second last iteration, we have only one node remaining connecting to the new node being added to the n prime. In the last iteration, the second step is not going to be called because there's no j remaining. So if we add all these together, this is the number of comparisons. N multiplying n minus 1 divided by 2. And this is in the scale of n squared, big O n squared. So big O here is actually to say that the Dijkstra algorithm in the worst case runs in the scale of n squared. That means the time complexity, the growing trend of Dijkstra algorithm is this. When n approach where the network goes really big, the time requirement goes in this trend, like an n squared curve. Now, if it's only big O n, the curve is linear, a straight line, sorry, the line is not very straight here. Now, there's an implementation available for Dijkstra algorithm such that we could do away with only n log n. Now, this is better than n squared. Right? So again, n is here, n squared growing really fast here, and n log n is actually kind of in between. Faster than the pseudocode we've investigated, and better than a linear algorithm. So, nice to have an efficient implementation, even though the original Dijkstra algorithm is not so good.
All right, so that was the computation complexity. We'll analyze the space complexity a little later. Okay, so the second video here discussing issues with link state routing is the oscillation problem. So that was the same slide. You see that there is actually an oscillation title there. Yeah, so link state routing computes based on link cost. Okay. And in practice, when you're calculating routes, you might want to define the link cost, for example, as the traffic load. Okay, so when the traffic load is high, the cost of sending more traffic over that link is high. Okay, it makes sense. Okay, defining the link cost as the traffic load, because that way then you will try to find another path where there's less traffic. Okay, it makes perfect sense. But if you run link state routing over such a definition of link cost, where the cost can change dynamically, given by the current amount of traffic, you would run into this oscillation problem. And that is what this next video is trying to explain. It's a little long, 7 minutes.
There's one very special issue with link state routing that's called the path oscillation problem. And it happens when we set the link cost dynamically based on the amount of traffic going on the link at the time. Now let me explain using an example. Okay, so we have 4 nodes in the example, A, B, C, and D. A is the traffic sink. Okay, all traffic goes to A. B, C, D are traffic sources. A generates one portion of the traffic and send it over past BA. E generates E portion of the traffic. E here is a very small amount, much smaller than 1. And C is taking the CBA path to send traffic to A. D generates also one portion of the traffic and it's taking path DA to send to destination A. And at this point, we need to update the link cost based on the traffic going on the link. So for link DA, amount of traffic is one portion. For link BA, amount of traffic is what? One portion plus the E portion from C. So total cost, 1 plus E. The cost for link CB, amount of E traffic from C only. You see also here, okay, this direction, BC, there's no traffic, therefore link cost is 0. Similarly for AB, similarly for AD, and similarly here for both direction in link CD. So we finish updating the link cost. After a while, link state routing is going to trigger Dijkstra algorithm running again. Right? As I described, link state routing is a dynamic routing algorithm. We do periodic update, and sometimes we use also network events to trigger recomputation of the routes. Link state routing there does periodic recomputation. Okay? It's going to recompute the routes based on the link cost now. So let's see. B here, we'll see 2 possible paths to go to A, right? One is to go counterclockwise to A, the other clockwise to A. So this direction here, the cost is what? 1 plus E, because there's only one link and the link cost is 1 plus E. If we take this other path, B, C, D, A, yeah, the path cost is the sum of the link costs, 0 plus 0 plus 1. Okay, so if we take the clockwise path, okay, to go from B to A, cost is only 1. And this is 1 plus E, therefore B is going to choose to go this way to send traffic to A. C also see 2 possible paths. Okay, if we take this direction, cost is E plus 1 plus E, and that is 1 plus 2E. The other direction, cost is 0 plus 1, therefore 1. And therefore, C will choose to go also clockwise to send traffic to A. Similarly, D sees also 2 paths. Okay, this direction here, cost is 1. This direction, 0 plus E plus 2 plus E, 1 plus E. So altogether, 1 plus 2E. So still, okay, this direction better. So D is also going to take the clockwise path, okay, the same path to A. So after the route computation complete, you see B, C, D all change to send traffic clockwise. And then we need to update the link cost again, right? So given the previous cost, we come up with the new routes, and we will then, okay, update the link cost, and we come to the new cost again. What is the new cost now? Okay, on link BC, yeah, there's only one portion of the traffic. On link CD, yeah, 1 plus E. On link DA, 2 plus E. Okay, that is why we see 1 plus E, 2 plus E, and all the rest of the links, 0. Once we update the link cost, after the next period that the Dijkstra algorithm is triggered, we compute new routes. So B will then try to see the cost to go this direction and the cost to go the other direction. The cost going counterclockwise is now 0. Cost going clockwise is now 1 plus 1 plus E plus 2 plus E. That's 4 plus 2E. So dominantly, BA is the better path. C's cost going this direction, 0 plus 0, cost is 0. The cost of the other direction, 1 plus E, 2 plus E, 3 plus 2E. So C is going to switch going this direction to send the traffic. What about D going this direction, 0 plus 0 plus 0? going this direction, 2 plus e. So d is going to switch for the first time to go counterclockwise. And that's why in the next moment, you see traffic beginning to change direction completely. Okay? From all clockwise, okay, one period before, to counterclockwise the next period. So given these new costs, we calculate the new routes all going counterclockwise, and we update the new costs again based on the traffic. DC is now 1. CB is now 1 plus E. And BA now 2 plus E. And that is what you see here. 1 plus E, and 2 plus E. As a result, B sees this pass costs 0. This pass costs 2 plus E. B switch the other direction. C sees this pass, really high, 3 plus 2E. And this other direction, 0. D, this direction, 0. This direction, super bad, 4 plus 2E. So all of them would switch back like this. And the link cost gets updated again. Okay. 1 on this link, 1 plus E on this link, and 2 plus E on this link, which is identical to 2 periods before. Okay? And you see the next period is going to be like, yeah, the previous period. And the traffic is going to oscillate infinitely, right? Clockwise, counterclockwise, clockwise, counterclockwise. So that is the path oscillation problem if we set link cost dynamically in link state routing. Okay, that's running the very straightforward Dijkstra algorithm. Just be careful here.
All right, so the route oscillation problem. You know what? The truth is that will still work. Yeah, the traffic will still arrive at the destination, except that the route the traffic takes will be changing constantly. Okay, and so the ordering of the packets arriving at the destination might be a little bit weird. Okay, I don't know how you like it, whether you like it or not. That is an issue. Okay, for specific type of applications, right? And that is also why that on the internet, the link cost is usually configured in a very simple way, maybe just a constant weight, okay, and never get changed, all right? So that was all the time we have today. There are actually 2 more issues. For example, we haven't analyzed the space complexity. Now, in order to analyze the space complexity, you need to learn a little bit better how the router learned the global information, learned the complete network graph in the first place using link state routing. So we have not yet talked about those, right? So that will be the first thing we talk about next week. All right, with that said, I say goodbye. And by the way, check out Yuqi's complete derivation table of link state routing and see if you can do the same thing and complete the table entirely. All right, bye.